We're going to move on to the next part of our presentation. As you've heard from Chris, we're looking for, CAD drawn electrical schematics, and here to talk about that is Mike Ashbaugh, a solid edge business development manager for Siemens. He had presented something similar last year, and so we're glad that he's back with us, and he's going to be joined by Mohammed Sajjad, who presented with you the mechanical drawing stuff last evening. So thank you, Mike, for being here.
Thank you, William. Let me just confirm, can you hear me okay?
Yep.
Great. And can you see my screen? I am sharing my presentation.
Yes, we have your screen.
Okay, very good. My colleague, Mohammed, who should be with me, is going to do the introduction for us, and then I'll continue with the presentation. So, Mohammed, are you with us this morning?
Yes, I'm here.
Good morning. Good afternoon.
Good afternoon, everyone, and welcome to the session, the Siemens session on how to develop great electrical schematics. So just a quick introduction, you've probably already heard, from William, but my name is Mohammed. I'm a solid edge application engineer, and I did a session yesterday on the mechanical design and drafting. And so today we're joined by my colleague, Mike Ashbaugh, who's the solid edge electrical design expert and who's going to be doing, electrical schematics. So Mike joined Siemens Mainstream Engineering in 2019 to support the business development of the solid edge portfolio. He has a bachelor's degree in electrical engineering from Penn State and a bachelor's in physics from Westchester University. So Mike has, 30 plus years of professional experience in design and simulation tools as an application engineer. So, it's very important to understand, that solid edge is so much more than just a CAD system. It has like mechanical design aspect like we talked about yesterday, but there's a lot more to it, right? And electrical design, simulation, manufacturing, technical publication, data management, and then, in today's age, the cloud-based collaboration, which is very important. So, but today we will focus on the electrical design aspect of the solid edge portfolio. Now, when we talk about the solid edge portfolio, it is consisted of so many different aspects of solid edge, which you can find all the details on the link that you see here. You can also scan the QR code, and you can also find, tutorials, guides, as well as curriculums, to be able to quickly learn how to use solid edge as well as solid edge electrical. So now I'm going to hand it off to Mike, and he will go into the electrical schematic.
Okay, Mohammed, thank you very much for that introduction. And William and everyone, I'm really excited to be here again. Thank you for inviting me. I want to focus on a particular tool in this electrical pillar of the solid edge portfolio. And as Mohammed said, you would have access to this. You can try it yourself. And the product is solid edge wiring design. And it's really used for this type of application that you're talking about here with the solar cars, looking at Chris and the wires connecting all the systems together. It's a really good fit for that. Mohammed mentioned my background a little bit. When I was first out of school, I did a lot of electrical schematics, and these were for printed circuit boards that we were developing for a satellite ground station. I also did schematics that go in field programmable gate arrays, very large chips that do a lot of things on a board. So in this application here, when I'm talking about solid edge wiring design, just to be clear, this is not for PCB board development, but the concepts are very similar. So here we're going to be thinking of, these wires and wire harnesses that we put into our assemblies. And wire design is a time-tested software that's used in our industry throughout the aerospace and automobile industries as well. So it's a very powerful tool. Now you should see my next slide here showing the smart connected products. And really this is just to convey to people that wires and electronics is in almost everything that's built today. right? You see the car on the left, lots of wires there, electronics, lots of detailed harnesses, lots of complexities. In the middle, here's a medical type machine in a hospital, lots of electronics in there. And the electrical systems have to get that right in collaboration with the mechanical team. We have this battery powered snowblower, for example, right? Looks pretty simple, right? But there's a lot of electronics that go into that. And on the far right is a vending machine, right? So all these things have electronics in it, and it's the solid edge wire design that I'll show you is a real good tool to help you capture that great electrical schematic. So you should be looking at my electrical schematic here, which is the hand sketch. And I kind of had to chuckle when Chris shared with us, how he starts. And yeah, if you're walking through an engineering building, a conference room, you could look on a whiteboard and you could see something like that. And just like Chris said, this is where people capture their ideas, maybe collaborate a little bit. And it is true, it is an electrical schematic. And some people just use this and move forward with their design process using this type of methodology. But without the intelligence in electrical schematic, right, we really do run the risk of not meeting our time guidelines, have a difficult time conveying to the rest of the team, what's the intent? What are we trying to do with this circuitry? Because we want to get it right the first time. So what's the challenge with doing something like this and not moving to an intelligent CAD system? Well, we certainly have the devices, we have the components, but they're really just lines and boxes. And so the intent of the circuitry is very confusing. So when we pass this along to our colleagues on the team, they have to be asking us questions. What did you mean by this? Right? What are the parameters of this particular device? What's the ratings? What's the part number? And Chris brought up a very important point. He said I think to quote him, he would like to have 20 copies of the circuitry, the schematic in his garage because he's always referencing it. So we want to use a system that allows us to get access to that through the entire design process. So that was a great example. And you'll see we can do that with solid edge wiring design. So just keep that in mind. People still use this approach and they stick with it, but it has a lot of limits because we can't share the intent. It's not very efficient, and we can't automatically drive the things we need from this, such as a bill of material to order the parts. We can't get the wire cut list, right? All of that has to be manually generated if we stick and use only this approach. So please keep that in mind. Now, if we compare what's it like to use an intelligent electrical schematic tool like solid edge wire design, here's an example of that. I'll actually show a video of part of this circuitry. We still have our components, we have our devices, right? The little purple boxes are actually the connectors that match to the devices, right? So we actually have a lot of information on here. The lines here are actually wires. So when we put an element down on this schematic, it actually has parameters and meetings and characteristics. So the line being a wire, it would have a color, it would have a gauge, it would have a length. And the devices themselves, they could have a part number, they could have a cost, they could have a performance rating, and could have a website where you can learn more about the part for the data sheet. And notice we have all that information available to us without cluttering up the schematic. So that's the key thing. All of these properties we can keep track of and capture are available when we need them, but they're hidden when we can read the schematic. So the advantage is here, right? I give this schematic to my colleague, he or she can read it. If they create a schematic with the same tool, I can read their schematic because we have a consistency of what the symbols look like. Now, when it's time to generate the bill of material, we have to go out and buy these things, or we were trying to determine what's the cost of all these parts. If we have that information on here, we would be able to generate that automatically from this schematic. So it's a really important value to engineering teams and companies. Now, I threw this slide in here, right? And I just wanted to really kind of make this point. The reason a topic like this is so important is because the engineering teams and the companies, they're always under some kind of pressure. Sometimes it's all three of these, right? The cost, the time to market, and the risk. Sometimes one's more of a priority than the other. But that is why customers look at, how can I do this better? Can we be more efficient? Can we get the answers earlier as we're starting to capture our design, because that'll lower the risk? And what kind of trade-offs can we do if cost is important? Right. So that's really important, why people look at how they're doing things today. Can we do it better? What tools should we use? It's always a part of the conversation. So the solid edge wiring design, which I'm going to show you some videos and I'll kind of explain some of the key highlights. The first thing is, it is an intelligent diagram. So again, what that means is, yes, it's a CAD tool, but when you put a component or a device or a line down on the schematic, it actually represents something like a wire, right? That's the key difference. We can have 2D CAD, right? We're using a CAD tool, but it doesn't have the intelligence behind it. This has the intelligence, and that's really the key piece there. Tied to wiring design is the centralized electrical parts library. You'll see that in my video demonstration. So when we start a project, we can immediately start adding symbols that we're pulling from a centralized electrical parts library. The reason that's important is all of us who are creating schematics are pulling from the same library. We know that those parts are accurate. They look like we want them to look. And so we get that consistency. The third item I have on here is styling. Styling is these tools, you can enable them and customize them so they look like your company's standards. And that's really important. Again, for legacy, for readability, large companies work in division, right? They have a certain style set. They want their title blocks to look a certain way with the company logo. They want to have the designer's name on the title block. The titles automatically count the sheets. They use the proper fonts when they label wires, the naming convention. There's so many things. And remember, this software is used for automobiles and airplanes where there's just miles and miles of wire, right? So this is very powerful software, right? But we can bring it to the solid edge in the smaller, medium-sized businesses and be very effective. Two other important things I want to call out at this time is design rule checking. What that means is, as we're creating this schematic, putting down devices, running wires, the design rule checker is running in the background to make sure that what we're putting down is electrically sound. So for example, if we have a component we put down, but we didn't wire it up, we could easily miss that if this is a multiple sheet drawing. There's no limit to how many sheets you have in a design. If there's 100 pages or 300 pages, you can't possibly find where you may have left a component and didn't hook it up. So design rule checker will help us with things like that. It's called correct by construction. If I'm putting down a new wire and I want to give it the name wire 2 and I've already used that name, it won't let me enter that in, right? Because we can't have a wire with the same name. If we're using drafting tools, none of that is an option. And then finally, a very important piece here is simulation. I'm going to show you examples of this. Simulation means, yes, we've captured our schematic, but do we have it hooked up properly? Will it function properly based on the way I have the switches set and the diagram and the schematic? So that's functional simulation. And it also works to do what we call a performance simulation, where it will look at the current and the voltage to see, am I meeting the electrical performances? And now, as I mentioned, my background, 10 years of doing printed circuit board design, there's a lot of simulators there that look into signal integrity, which is a whole nother aspect. But these tools are really fun, and you can really learn a lot. It's been quite an adventure working with this tool. So let me just show you so you can see what solid edge wiring design looks like. And as Mohammed said, if you ever try the tool through the academic bundle and try that, we have tutorials that'll walk you through how to create this for a schematic. But I just want to show you how easy it is to create that first project, that first design, and now all of a sudden you're putting parts on that drawing of yours. So here the user creates their project, which is called test drive. And then a window comes up and you give it the design name. In this case, door locks. And we're going to give the first sheet name sheet 1. Now, as soon as we do that, let me just pause the video here. Now, as soon as we do that, our drawing area is off to the right-hand side. And notice it already has the title block. So it'll put our company logo in there. If we're going to work with a C size sheet or a B size sheet, whatever we want to do, it puts that in there. And as we add more sheets, they're automatically put in and they're counted. On the left-hand side, here's where we start to see the structure of our project. Test drive, the name of the design is door locks. And now in the lower left of that browser, here's where our access to the library is. You'll see the user here is going to add some symbols to create that very simple first circuit. But we could also hit the parts tab and search through the library and add specific parts. Right, so let me have this continue. We'll see how easy that is. Select the symbols tab. These are the libraries that we can look through: batteries, antennas, capacitors. And when we find a symbol we want to place onto the schematic, we get a preview, which you can see on the lower left. Said, okay, that's the battery symbol that I wanted to put down. So we just put that onto the schematic. Nice and clean. Here the user's looking for a switch. Type switch in the filter. Now the system is going to query our centralized library, which is a database, and said, here's all the switches you can select from. We identify the one that we want, and then we place it onto the schematic. Next thing is a lamp. It's a simple little lamp circuitry. Found a lamp and put that down. Now, while we're doing this, right, the system is capturing what's in this design. Now we have 3 components already, right? We just added a ground, and now the user is going to run a wire. So we pick the wire. There's capabilities in here to do auto routing. You see it automatically put in the 90-degree bend for us. It knows it's a wire. We can turn that routing off depending on what we want to do. And then here we have our schematic. Let me just pause right there. Right, so real simple. If we want to go in and change the names of the components or the names of the wires, here's wire 1, wire 2, wire 3. Right, again, if this was on multiple sheet drawing, it would make sure that we didn't use the same wire name twice. So let me just let this finish for another few seconds. And all they're doing here is just going to label these components with some more informative name for the particular design. And there we go. That's the first schematic, real easy to do. And what's important there, if we have multiple schematic sheets, this can get very complex, and you have the ability in that browser to highlight between the design browser and find the information on the page. This is a very common feature and important feature for intelligent schematic tools. Now, with that created, right now, immediately, without doing anything else, we can actually analyze that circuitry. So I just wanted to show you this. This is when simulation and CAD gets fun here, when you can do the simulation. There's a lot of tools in engineering that do simulation. So here on the lower left, the user will hit analysis, and that will start the simulation in the background. Hit analysis and then run the simulation. Now, when it started, let me just pause this here real quick. When it started, you notice that the wires turned from black to cyan. And what that means is the simulator is running, but there's no current going through that circuit. If there was, it would be green in color, and it's not. And the simulator here allows us to set the parameters of each of those components, the battery, the switch, and the lamp, because models are provided for these components in this application. So you're going to see the user be able to hover over one of those components and toggle either switch on and off or something like that. That's done because we have models associated into solid edge wiring design. So a couple things to point out and just make very clear. Notice that we don't have to clutter up our schematic with a bunch of simulation models that you have to see. All of this is buried and hidden, and that's the value of an intelligent schematic. If we go back to our whiteboard and that hand sketch, whether that's on the whiteboard or we did that in PowerPoint or some other 2D CAD tool, we can't do this, right? So when the design gets more complex and the engineering team gets larger, we want to have new tools that enable us to do that. So I'm going to continue with this video, and we'll see that they'll realize that the lamp isn't grounded, right? And they need to close the switch. So let's see them figure this out and then get the circuit working properly, which will turn green. Start the analysis again here. So they hover over the switch. They're going to check the position of the switch. It's open. What happens when we close it? Circuit did not turn green, so we're not getting the results that we want. And then recognize, oh, our lamp is not grounded. So we put in the ground and we wire that up. See, this is an example of functional simulation. If we're designing, we want to make sure we don't skip a wire or miss something, because if we're building prototypes and we don't update our schematic, we're not going to find this out until way later when other people are looking at the prototype, and that's could be costly to try to fix that. So here they close the switch, and then we find that the lamp is actually working. So that's an example of simulation here. This next thing in a simulation is to look at the numeric simulation. As I mentioned, this is where we can see the current values and the voltage if you want to look at that. In this case here, the user's looking at the model to say, is there enough power for this lamp that we've selected so it will light? And the answer is yes. Again, seems pretty simple, but again, if we can get this correct now in this environment, that reduces the risk. Think back to our cost, our time, and our risk. This is reducing risk because we're validating that this is going to work, building our confidence. Chris talked about wire sizes here too, right? So we want to, you can check to see how much current's going through the wire. The reason that's important is we want the wires to be the right size. Again, if cost is an issue and a priority for what we're building, what we're selling, we don't want to over design the system because we are kind of spending too much money to deliver that, right? So we want to have that optimized. It's a really key important feature why we look for these tools to help us. Okay, that was what I wanted to kind of drive home when it comes to using an intelligent schematic versus a 2D drafting tool. But if we use an intelligent schematic tool, this is what it buys us: the ability to collaborate together between the electrical system and the mechanical system, or the electrical and the mechanical engineers. So I wanted to talk about the traditional approach, right? How people historically have been doing it, and many still do today. But then the new methodology that we get because we decide to adopt something like solid edge wiring design, where we can collaborate between those two teams. So here's how this looks. In the traditional approach, we have the electrical and mechanical engineers. They're really working in two different environments, and it's difficult for them to communicate even about really simple and basic things. So we have the young lady, electrical engineer on the right. You know, she's working on her schematics, and you can see she's in isolation, separated from her mechanical engineer on the left, because we have that big break in the picture, right? So if she is doing her schematics using a drafting tool or an unintelligent tool, if she makes any changes or changes are required, it probably takes her a lot more time than it's really necessary. It's very manual and it's very tedious. And without the intelligence built into her diagrams, when she tries to communicate with the MCAD team, the mechanical team has to enter in that data. It has to be recreated. And that too is very time consuming and it's error prone, right? If we're trying to build efficiently and quickly, stay competitive, right? That's trouble for us. So without true co-design between the mechanical and the electrical engineers, any issues that we find, they're too frequently only identified very late in the design cycle. And this is critical, right? What happens if we find out late that we need some design changes? You know, what are the options available to us? Well, often any options are few, right? And they're certainly more costly to implement. And simply, you might find yourself that you don't have enough time to make the changes and still meet the scheduled milestones or market targets, right? So that's, again, managing the risk. We want to be able to find out quickly if there's any issues. So the earlier, the better. So the better way, right, to create and enable true co-design across these disciplines, we use new software and new methods. And this way, the engineers, they're free to innovate, and they can actually study the impact of what's the trade-off and the changes. If I make this change in the electrical system, what does that mean to the mechanical team? Staying in their own tools and communicating. That's really what we're striving for, so we can be efficient and stay competitive. Okay, I want to walk through like the data flow, what this would kind of look like, kind of again, focusing on the collaboration. And then I'm going to show you a video demonstration of that. So since you've seen wire design, right, how does that work? So the user begins, as I showed you, they're going to create their diagram in solid edge wire design. They're going to select their symbols and parts from the built-in electrical parts library, right? So they put down their devices and now they're going to connect them up with wires. But the electrical parts library, that is the foundation of solid edge wiring design. That library is going to define the relationships of the parts, and it helps us automate building that wire diagram and helps us preventing from re-entering the data. So this is a really important aspect of wiring design. Remember, we have design rule checkers running in the background, right? It's going to check to make sure we don't have duplicate wire names, going to make sure we don't have symbols that are out of date, or maybe parts that are not connected. And there's a lot of other things that it can check too. And then simulation. If we want to simulate, we can do that anytime. We can do both functional simulation and we can analyze the wires for their current and their voltage. Okay, so that's the electrical team, right? They're doing the work, they're feeling good. Now, their wire connectivity can be shared with the mechanical team using what we call bridging out. And this is enabled through what we call connected mode. Connected mode is a term that we use at Siemens, and it's describing this bidirectional communication between the electrical system and the mechanical 3D models. Now we can do this as long as the engineers are on the same network system. They don't need to be in the same building. They can work across the world, right? But once the electrical connectivity, the wire diagram that I showed you, right, that can be sent over through connected mode and shared with the mechanical team. So now the mechanical team, they're in solid edge MCAD. They can bundle the wires into harnesses. They can route them to meet all of their mechanical constraints, whatever those are. Now, once they're done completing with the routing, now the wire lengths, we know more about the wire lengths, so we can communicate that back to the wire diagram automatically, again, using the connected mode, and we call that bridging in. So automatic, real quick, can do it anytime you want. Now the electrical team has new information. The wire lengths have changed, not the connectivity. So now the electrical team may decide that, hey, I'm going to run a simulation. Let me just confirm that nothing has changed with our performance. Tie all that loop together because we can share information because we're using intelligent applications. So here's the key, the bidirectional communication. It's easy to set up and perform. And this is the capability that's going to help us reduce and eliminate those late state design changes because we enable that with this new methodology. So if we look at this big picture of the data flow, this will enable the new methods and help meet the challenges of today as these designs become more and more complex when it comes into the electrical content. One final comment here, again, comparing this to our non-intelligent hand-drawn sketch schematic, right? Here with an intelligent wiring schematic, we enter the data only once, and then we share it where it's needed and when it's needed. And in Chris's example, he wants to view those PDF schematics, or he wants to view them anytime. We can generate a PDF output of the wiring design. We know it's correct. We know the wire lengths, and we can generate a PDF, and he can look at that on his iPad or anything else. It's a PDF, and he has that information, or he could print it out. And we know it's correct and it's accurate because it's automatically generated from the schematic itself. That's why this is so important.
Hi, Mike, I have a question for you with regard to the parts library.
Yeah.
How detailed is that? Are there off-the-shelf components? We talked about some solar car components like a power tracker, things like that. What level of detail is that library?
Yeah, there are a lot of library parts, but whether you have what you need, we'd have to look into that. So when someone uses our tool, it comes with the starter library, and then we have other libraries that can be added to that for other industries typically. But here's more what people typically do. Engineering teams add their own parts, right? So maybe they just put in the symbol or their part information. That's the other thing. The users often add to their own centralized library, right? Because they want to make sure it's correct. They want to make sure it meets their drawing standards. That's typically how that works. So if you don't have the part that's provided, right, you have the ability to add what you need. That's a very common question, by the way. Any other questions?
Nope, I don't see any other questions right now.
Okay. Yeah, thank you. I'm not watching questions, so thank you for doing that. Okay, so in this video here, I'm just going to show the connected mode. And the idea is very easy to do. And because it's easy, the teams will use it, right? And that's really the key part. Because they can collaborate and it's easy to set up, they're going to do it. And the opposite's true. If it's difficult to share information between the electrical and mechanical teams, they will not do it frequently and they're going to wait because it's too tedious, it's too error prone, it's too disruptive, right? That's what we're improving on here. So this is a very short video. This is the schematic, and what's going to happen here is, the schematic and the mechanical team have already been communicating. And in this yellow box here has been new circuitry and components that have been added. So we just want to update with the change. Again, because we're working together, collaborating, this type of information is very easy. We're going to do the bridge out to get that information to the mechanical team. So let me just move forward a little bit. Here's the mechanical environment, the solid edge. Okay, let me just pause right here. Okay, so we have our schematic on the left-hand side. This would be solid edge wiring design. Now on the right-hand side is solid edge MCAD, right? Different tools, different teams. They may even be in different states, right? But they're collaborating together because they're on the same network and they have the ability to use the connected mode. So the electrical team on the left, they're going to say, I want to bridge out. It's up here if you can see my cursor. They're going to bridge out and send the new information over, and the mechanical team will accept those changes. So let's just push this forward a little bit. Okay, there's the bridge out, and then we get a report. These are the wires and connectors that we're sending over there. So we continue, and then we get into the MCAD side, and I'm going to stop here once it's accepted. Okay, right there. Okay, now that information, the new electrical information was sent over to the MCAD team. They accepted it, and now we see the new wires that were added, and they're just connected, but they're not routed where we want them routed, right? So what happened there, right? That was automatic. We didn't have to do anything manual. We know the connectivity in the mechanical model is matching our electrical schematic. So now the mechanical team can go off and do their wonderful things. They're going to run this wire so it's out of the way wherever they wanted it. So let's let them do their work quickly here. This is done with a feature called electrical routing. This would be the job of the mechanical engineer typically. Okay, I'm just going to pause right there. And that's the process of them doing this. So as this wire is being routed, the length of the wire is changing. We don't really know what it is until the job is done. So once this gentleman or this lady finishes this task, they'll say, okay, let's bridge this information in. It's called bridge in, and now update the electrical schematics with the new wiring information. And that would be the next step here after that. And we can enable all of this because we're using the connected mode. Okay, so I wanted to make sure that I showed that to you. So as a reminder here, right, about the importance of collaboration, right? So this is the mechanical engineer. This is their environment, the connected mode. But I just wanted, what are some of the things that team is thinking about, right? The wires, right? Could they be rubbing on some of these mechanical components, right? We got an arm that moves, a door that shuts or whatever. Are the wires running in such an area that they could be rubbing and we'd have an issue, right? Is there an area in our assembly, whatever we're building, is it wet or cold or hot or something like that, that could cause damage to our wires and we'd have electrical failures? They're looking for those kind of things. Do I have enough room for the harness? Here, going back the size of the wires, right? We don't want the wires any larger than they need to be. They're more expensive. The harnesses get thicker, right? And it's more costly. So we're really optimizing. So these are the decisions that the mechanical team can make because they have this information from the electrical team. So from the electrical team, right, what are they thinking about? What keeps them up at night, right? What about the signal wire? Do I have enough strength with this new wire length to reach my devices so it behaves properly, right? They're trying to answer those questions. Are the wire diagrams sized properly? And fuses, there was a discussion where Chris talked about fuses, right? Are the fuses the proper size? And again, depending on what our priority is, right? These may be, maybe we have a lot of margin for error. Sometimes the margin is very small. So engineers are always asking, how small can it be, but be confident that it's going to work consistently, right? That's really the kind of thing. What's my safe margin so I know this will work given the product and where it's going to be and the nature of it using. So those are really important things that both of those teams are thinking about, and we enable it because we're using intelligent tools that can share information automatically in a bi-directional communication. So this example here, you saw this schematic here. I'm probably not going to play any of this up, but I'll just kind of describe. This is just a video that I kind of prepared. And really, it's just more collaboration. This is an example of circuitry that's part of a tractor cab electrical system. And it's multiple pages. And it just walks through here doing more simulation. It'll look at the switch positions here to see if the lights are being lit up like they're supposed to, right? That would be the functional simulation. And they're going to find that there's some switch on another page is not turned on. So their simulation wasn't working properly. They'll find out that there's some wires crossed here, and it's just showing another example of the collaboration. So I don't think I'll go into that, but I just want to convey to you, you can have more than one electrical engineer working on some of these larger systems. So if you get an opportunity to try solid edge wiring design, it's real easy for the smaller engineers, the smaller teams, the individuals, right? But it's scalable to have the larger teams with this same software. So that's really why I wanted to put that in there. The video also goes on to show that you can document your changes. That's also important. Maybe as you're developing your solar cars too, you're documenting what you had to change and who changed it. These tools help and enable that. They keep track of the changes for you. You can put notes on who did it and at what time. Okay, so let me just move forward here. Just a couple more slides, and then I'll finish up here. So my big message today, if we want those great electrical schematics, we want to use an intelligent diagramming application. That's the first thing, right? Lines and boxes need to be more than that. They actually have to represent devices and wires, and they have to have properties. And if we do that, we're putting ourselves in a really good situation for downstream efficiency to share the information with our colleagues. Design rule checking, that helps us as we're capturing our schematic to help catch things that as humans we miss, and we want to take away that manual checking if we can. Simulation, right? Let's have some confidence that we actually are not missing a wire or two or a ground or something like that. It doesn't take much, and we built a harness only to find out we're missing 2 wires, right? That's very costly, and if we're in a really tight competitive space, time to market, right, that's critical, and that could make the difference of whether we can sell this product and get the market share we need or not. And documentation, I kind of go back to what Chris said. It's a perfect example, right? If you're in the field, you want to have access to the schematic sheets, great. We can automatically generate those details right from the schematic itself. We don't do it manually, right? You don't have to ask yourself, is this the latest version or not? You pull up the tool, you generate the PDF, and you share it with those that need it. You print it out, or you can look at it electronically. And some of these tools have intelligent PDF, which means you look at the PDF and you can see all the properties associated with the wire and the device as well. And then finally, the collaboration, right? Working together, electrical, mechanical, that new methodology, right? It really helps us stay competitive and reduce the risk. And then finally, optimization. I didn't really stress that word too much, but when we talk about simulation, we talk about having virtual tools to help us. That's what allows us to optimize, right? Optimize, in other words, study the questions. What if I did this? What's the impact? And we could find out the answer to that. Someone suggests, what if we did this, right? Is that a better option? The virtual environment, being able to quickly change and test these things, that's what allows us to optimize, so we're confident why we're going down the path. This is, again, I spent a lot of years in the industry doing a lot of simulation of electrical circuits and signal integrity, and this is always what we're striving for, right? Why are we making the engineering decisions we are, right? And you have examples and you have measurable simulation results to point why you went that direction. This is a slide that Mohammed talked about earlier. This is the Solid Edge Academic Portfolio, the 7 pillars. These are all the tools that you'll find in each of the pillars that they're available to you. And then here's that link again, which is also on the next page. I'll just make a comment. If you are going to try the solid edge wiring design, there are tutorials that come with that. There's other material, getting started material that some of my colleagues have created when people like to evaluate the software. One particular example comes to mind where it helps you create your first wire schematic to create your own title block. And there's a video that shows exactly how to do that. It's one of the very first things someone would want to learn about solid edge wiring design. And it just seems like it might be a good fit for folks working on this solar car program here. And then finally, this is the slide that Mohammed showed earlier, right? We encourage you to access the Solid Edge portfolio and those available resources. And finally, thank you. Before I open it up for questions, I do want to say that it's pretty impressive to have high schoolers work on the product like this. That was not my path. It was not my journey. Just real quickly, I went out of high school and I went into the United States Navy as a musician, and I was stationed in Europe and for 4 years. And then when I was out of the service, I went to college and I got my electrical engineering degree. But my point, I guess, is we all have a different path, and engineering's been really fun. I designed for a while, satellites, and spent the last 20 years kind of selling and working with customers on design flow and things like that. So I just wanted to encourage anyone that there's a lot of space in the world of engineering to do a lot of different things. You could design, you could be in marketing, you could be in sales, you can be in support. So I'm really happy for everyone, and it's you must be incredible people to be in a program like this. So thank you for allowing me to participate today.
Thank you, Mike. We'll open up for questions, but you know, I think it's great to see just the type of capability that the intelligent design provides for solar car teams, especially when you think about some of the complex circuitry that we're going to have with cruise control. Not that you could use it for a road race, but on a track race, you could do cruise control, and then you need to make sure that the cruise control engages or disengages at certain times, or with some of your lighting. And so I just see so the great capabilities that the software brings, and I hope that the solar car teams will get a chance to use it.